So some type of problems that you could differentiate without the chain rule. This one's pretty easy, polynomial, right? That's on freeze. A couple problems you could differentiate without the chain rule. Say y equals x squared plus 1, easy polynomial, right? Obviously, trig function, we can find the derivative of that pretty easy. Pop quiz, what is the derivative of sine? Sine. Okay, another polynomial, linear function. And then, okay, we have a sum or difference problem. That'd be 1 plus what? Secant what? It's the derivative. Secant squared, yeah. Y prime equals 1 plus secant squared of x. Okay, now with the chain rule, we would need the chain rule for something like this. Okay, definitely need a chain rule here. Why? Because we have a composite function. Good luck expanding x squared plus 1 to the 1/2 power. Good luck doing that. You'll notice we didn't have any arguments inside the trig functions, like sine of 6x. We need the chain rule for this one. Okay. Similarly, this is much easier with the chain rule. Okay. And this one, there's a composite function. There's a function within the trig function. So we need the chain rule for this also. Okay. Well, there we go. Here's a chain rule. Now, if you look at this, we have f of g of x. It's definitely a composite function. Inner functions g of x, outer functions f of x. The derivative of a composite function is the derivative of the outside function at the inside function times the derivative of the inside function. So the derivative of the outer function and then I say at the inner function times the derivative of the inner function. Okay. So it's the derivative of the outside function of the inner function times the derivative of the inner function. Now there's some stuff underneath the shade. We'll go over that later. We're just going to work on mechanics today. Here we go. Find dy dx for y equals quantity x squared plus 1 cubed. For those of you guys that just hate Pascal's triangle, this is for you. Chain rule is for you guys. All right, outer function, cubed, right? Some stuff cubed. That's the outer function. Inner function, x squared plus 1. Okay, so again, at the very beginning, I might write this out a little bit more. After we know the rules a little better, we'll just find the derivatives and not write out like d dx. Okay. If we needed to rewrite this, again, that's not the derivative. That's just a rewrite. But once you start taking the derivative, then we write y prime. All right. So derivative of the outer function. The outer function is quantity cubed. Well, that's a power, right? So we take or use our power rule. 3 x squared plus 1 squared times the derivative of the inner. I'm just going to write out d dx of x squared plus 1. But in the future, we're just going to find the derivative of the inner function and write it down. Okay. 3 x squared plus 1 times, okay, what's the derivative of x squared plus 1? 2x, there you go. All right, I can move some things around. I think it's appropriate to multiply 3 and the 2 and then bring the x in front. I think it looks a lot better. So we have 6x times x squared plus 1 quantity squared. This is a very nice factored form derivative. Do not expand this in combined like terms. Just leave it factored, please. All right, pop quiz. Where would a horizontal tangent line occur? Well, we have to set the derivative equal to 0, right? 0 equals 6x, x squared plus 1. And then we're already in factored form. Just use the zero product property, right? 6x equals 0. I'm writing this out because with talking with some of you guys, we're missing this. We're missing this part, okay? And then we have x squared plus 1 quantity squared equals 0 using zero product property, okay? This part, x equals 0, and we should get to the point where, like, you look at this, x equals 0, and then x equals, well, when does this become 0? Well, does this ever become 0 here? This is always going to be positive, isn't it? So that's never 0. Okay, so this does not give us a 0. The only spot at which we would have a horizontal tangent line would be x equals 0. Again, we can find the height by plugging in 0 up here, and that looks like 1. So that horizontal tangent line would occur at 0, 1. Okay. Who likes this way better than the Pascal's triangle? Way better, right? It's pretty quick, isn't it? Okay. We just got to be proficient with these rules, be able to do these derivatives pretty quick, and then do something with them. Okay. Any questions on this? All right, let's practice it a couple times. Same thing. Go ahead and give it a shot. See what you can do. All right, see what we got. I don't think we need to rewrite this right now. Pascal's triangle actually would be kind of annoying. There's a lot of algebra mistakes waiting to happen with us expanding this. Thank you, chain rule. F prime x equals, okay, derivative of the outer function. Outer function we identified as a cubic function, right? This stuff cubed, right? So the derivative of a cubic function would be 3 times the stuff on the inside squared times the derivative of the inner function, which would be, or minus 4x, like that. Okay. And honestly, should we rewrite this? Could we distribute the 3 through this? I like this better. But just be aware there are various other forms of the derivative. Maybe they distributed 3 through and got 9 minus 12x. That's perfectly fine. Okay. We don't try and distribute as least amount you can unless it's in a fraction where we combine like terms, stuff like that. Okay. We could find the 0, set this equal to 0, set this equal to 0. We can find the zeros of the function, the zeros of the derivative. That's it though, leave it like that. If we expanded this, so we had a whole bunch of terms using Pascal's triangle, the derivative would look a little bit different, wouldn't it? That's okay. If we took this derivative and expanded this derivative and then multiplied through by 3 minus 4x, you get the same thing eventually. Right? It's just different forms, and that's okay. This is better. All right. Find all points in the graph of f of x equals the cubed root of quantity x squared minus 1 squared, for which f prime of x equals 0, and those for which f prime of x does not exist. And instead of points, we know how to find points. Let's just focus on x values. Let's find out the x values for which the derivative equals 0 and for which the derivative would not exist. Before we take the derivative, let's rewrite though. This is going to be x squared minus 1 squared to the, what, 1/3 power? Now we have an outer function 1/3, an inner function squared, and then an inner function of x squared minus 1. Well, let's take care of this power to power. That'll simplify things a little bit for us. Okay, power to a power rule means you multiply the powers, right? So it'll be 2/3. Okay. Now we have outer function, which would be the 2/3 power, and then inner function x squared minus 1. Okay. Well, let's see what we can do with that. F prime. Okay, the derivative of the outer function at the inner function. 2/3 at the inner function. And then with that 2/3 minus 1, negative 1/3, times the derivative of the inner function. Derivative of the inner function will be 2x. Okay. Let's see here. Can we simplify this at all? I think this is a negative power, so that goes down in the denominator. That'd be negative, or no, it'd be 1/3 now. And then a 3 is down there, and it looks like we have a 4x on the top. When does this derivative equal 0? When the numerator equals 0, right? So f prime x equals 0 when 4x equals 0, right? And then x equals 0. So the derivative equals 0 when x equals 0, right? It means we have a horizontal tangent line at x equals 0. We could plug in 0 up here, get an answer, and we can have a point actually, right? I don't want to focus on that. That's pretty easy. When would this derivative not exist? Yeah, when the denominator is 0. So f prime dne when, let's see here, 3 times x squared minus 1 to the 1/3 power equals 0, right? Okay, what makes the bottom 0? What makes this 0? 1 and negative 1, right? Now, how can we do this algebraically? Well, I'm hoping you guys can see, well, this is x squared minus 1. It factors x plus 1, x minus 1. So therefore, negative 1 and positive 1 make the denominator 0, right? Or, okay, multiply by 3, you get x squared minus 1 to the 1/3 power equals 0. Cube both sides, x squared minus 1 equals 0. And then you get x minus 1, x plus 1. But honestly, we should be able to avoid some of these steps by identifying, okay, that's the difference of squares. If this is 0, 0 cube root is going to be 0 times 3 is 0 too. It's okay to pass up some of this math. It's all right. You should not have to show all that work. Okay, so we get x equals negative 1 and x equals 1 when the derivative does not exist. Okay, it's always a good idea to make sure these x values make the function exist, especially for when you find the derivative equal to 0. Okay, what does this mean? It means maybe a vertical tangent line or a sharp point or something's happening. At x equals 1, x equals negative 1. If you graphed this function, you would see that. Okay, you'd see a horizontal tangent at x equals 0. Okay? Any questions on that? Last one. Before, the only way to do this problem would be to use the quotient rule, correct? But now we have the chain rule. I try not to use as much as I can. So let's rewrite this in a different form. Negative 7, 2t minus 3 to the negative 2 power. Okay? Scalar multiplier negative 7. Looks like we have outer function negative 2, inner function 2t minus 3. It's good to look at your function and ask yourself what's going on, so then you can prepare mentally to take the derivative. G prime equals. All right, this is a composite function. We clearly know that. Therefore, we're using the chain rule. Okay. The negative 7 staying there is a scalar multiplier. We're taking the derivative of this. It is a power. Outside function is a power. So use a power rule for your outside function. So times negative 2 at the inner function. And then minus 1 from negative 2. What's that? Negative 3. Times derivative of the inner function. Derivative of 2t minus 3. This is 2, it looks like, right? All right, cleans the garbage up a little bit. Negative times negative is positive. 7 times 2 times 2, what's that, 28? 28 on top, and right away, using my critical thinking skills, I notice the negative power. I'm moving that into the denominator. You don't have to just like try and clean it up all in one step. You can write it out a couple times if you want to. Okay? Not bad, is it? Way easier, right? Way easier than the quotient rule. Last year, I made the students write out the quotient rule first and then use the chain rule. And they're like, yeah, we like the chain rule. Because sometimes once you learn a rule and you're kind of comfortable with it, you don't want to learn another rule. Like, nope, this one's much better. All right. Does g prime of t ever equal 0? Do we have a horizontal tangent line ever occurring for this derivative or for this function? No. Does the numerator ever equal 0? That's what you're asking yourself. If I ask you, does the derivative ever equal 0? Look at your fraction. Can this ever equal 0? No. So constant is 28. It's never equaling 0. Is the derivative ever undefined? Does the derivative never not exist? Where? Well, wherever this equals 0, right? So 2t minus 3 equals 0. Add 3 divided by 2. The derivative will not exist at 3 halves, right? What else do you know about 3 halves? Well, think about the original domain of the function. Well, the function exists at 3 halves. Set that equal to 0, and that's 3 halves also, right? So the function does not exist at 3 halves. Well, your derivative better not exist at 3 halves also, right? Okay. All right. It's kind of nice taking some of these questions just a little bit further. It just prepares us for success in later chapters.